be for ICCV next year. We're excited to have you, Kristen. Take it away.
All right, thank you so much. Really great to have the chance to share some of our work with you. And I'll be telling you about how we're coming from the computer vision perspective to try and influence agent behaviors in a way that would help scale robot learning. So we're interested in agents that can operate in human environments, whether that's using objects that are geared towards people or environments that are geared towards people. And this gives great motivation for looking to people and people's experience as a way to benefit robot learning. We're also interested in tasks that will be complex to the degree of asking not only to understand what objects are and how to move in a space as we map it, as important as those challenges are, but also to be able to answer questions like, what's possible with what kind of object? How do I achieve a goal given, and what are the objects I need to interact with to do that? And so this leads to all these questions and possibilities for learning from the visual stream how things work and how we can achieve a given interaction. And we know that learning to interact can be expensive, is a very hard challenge. So if you look at current reinforcement learning-based models that are showing a lot of interesting progress, they're looking to learn from finding the configurations and the environment state and the agent state that would be successful, which can be notoriously sample inefficient. So then we can think of ways to inject imitation, including demonstration-based learning, which will accelerate that process. However, has its own certain expenses, including the possible need for expert teleoperation in the agent's domain, possibly specialized hardware, and kind of this step removal of human action into the robot action. So this motivates kind of the approach that we will take in the work I'm going to show you in this talk, which is, as much as we can, learning from vicarious visual experience, particular video, and then whenever possible, first-person video, like this wearable camera here, which is going to reveal to us how smart agents like people can do things like move in the space, direct their attention, interact with people, and most importantly, in my examples today, interact with objects. So we're looking at video as a source of expertise that's passive, that's inexpensive, and that we'd like our agents to try and start from before their own physical experience. Okay, so how can we learn by watching people interact? I'm going to show you examples for visual affordances, for grasping based on those affordances, and for sequential visual planning tasks that leverage activity context learned from people. And so throughout, we're coming from the computer vision standpoint to start, and I'll be showing you though how we translate that into action for our agents. In our case, thus far with simulations, both with dexterous hand robots and with visual planning robots that have high-level abstracted action spaces for the latter. Okay, so let's look at interaction hotspots. Here, we're motivated by being able to look at objects not as something that we stop at naming, but that we stop only once we understand how to use them. So it's that difference between saying, hey, that's a lamp, or hey, that's a lamp, perhaps, but here's where it looks like I could toggle something, this looks adjustable, and so on. Of course, this is the notion of visual affordances, the possibility for action with an object. Now, if you look at current approaches that take a visual input to try and address this task, the approach has generally been sort of traditional supervised recognition. So you could label images, have people label where you hold a book, where you turn a page, and so on, and then learn to infer these on new examples. It's a little bit expensive for sure, but more importantly, it's got this indirection where what we label on an image may not be as rich or complete as what we actually do with objects. And so we've been exploring how to take video as the thing from which we learn these kind of afforded regions. And just think about how direct this could be if we are successful, because now it's about watching people, their direct activity, not in an annotation-based way for these regions, but then discovering what those regions are. And we've had early models to do this where we take video for which we know actions that are taking place. So think of this as a weak label, nothing about where hands are or where the regions are, but just watching actions that we can learn to recognize. And then we build on networks to discover how to anticipate the link between what an object looks like when it's at rest, because that's when the affordances take place before we start interacting, and link those kind of visual cues like the closed microwave in the top left to the state of the object when we're learning to recognize this interaction, like opening the door. And so we train models that understand actions, but furthermore understand how to anticipate actions that are possible given the object at rest. And when we do that, we can also localize the regions from the object image that are most responsible for that possible action. And we do this by what's called like class activation mapping, going back to the image to see the regions that are most responsible for tilting that action decision. So for example, you could say which regions look pullable, which regions in this image look pressable, and we'll get back through these interaction hotspot models a heat map saying where those seem to be. Now we take these hotspot models and we've been testing them on data sets like Oprah, which is YouTube product demonstrations, or Epic Kitchens, which is a first person in the wild video collection. And very importantly, we test hotspots not only for new instances, but even new categories. And the thought is, if we have agents that can look at objects that haven't even been encountered before, some new appliance, some new toy, but they can still understand what the functionality is, then they'll be able to act in more scaled up manner with new objects and for new activities. And so first, let me show you what hotspots look like here for some of the most common verbs. You see color coding, like green means it looks mixable in the center of that bowl, but also the pot behind it. Here in this sample, we see that the knife looks washable, the faucet looks adjustable. And these are things that are anticipated even without the action happening yet, as you can see with the knife on the left. And then finally, here's some jars that look openable in cyan there. The door looks openable as well. And of course, the key is now we're seeing the world in this first person perspective through the eyes of the agent that needs to take action. And so it's not enough to say that's a door and a jar, but here are the things that I think I could do and where could I do them. Now, of course, we've evaluated all the kind of heat maps like I was just showing you. For time, I'll keep this as a snapshot to say that on both data sets, compared to alternative weakly supervised models, we have a very strong advantage. And we're getting close to really compete with something that's heavily supervised, where you do that kind of manual drawing to train such a prediction model. Okay, so I've told you about how we can give an example here of taking video and learning from people how they use objects and where. Now let's build on that to influence robot grasping. And we're particularly interested in dexterous robots' hands. So multi-fingered 24-degree of freedom agent that's going to have an embodiment that's relatively similar to that of a human hand, which is really enticing because all these objects, many objects are made for human hands and require that dexterity. And furthermore, this is the kind of lineup that we expect could allow us to do this process of learning by watching people. So dexterity is super appealing. The action space is very complex. And so we do really have a strong motivation to reduce the sample inefficiency and to shortcut learning for agents like these based on human experience. And so here's our idea. We would like to discover not only the affordance regions like I just showed you, but also the human hand poses that are effective for human use of different objects. Okay, so how do we use our hands when using a pan versus a knife or an axe or anything else? We're going to watch for that information in video again, and then we'll translate it into the action of an agent that's trying to do grasping tasks here. And our approach will look at YouTube videos, in this case, in the wild samples, like the one you see in the top row. And then we'll use a dexterous robot hand, again, in simulation thus far, to start to build up these behaviors influenced by how people are using their hands and how those affordance regions are placed on an object. And if we did this well, the things we're seeking to come back are faster learning. So rather than purely reinforcement learning of this hand kind of bapping around at the object, we want it to have a leg up from this prior, can lead to more successful grasping policies, and just like before, requiring generalization to new objects that haven't been encountered before. So first, let's look at what comes back when you start to get a hand prior from video. So this In this case, we're using the 3D hand pose extractor called Frank Mocap that's from existing work. We chose it for its speed and its good effectiveness. And that's what all those blue hands are. Those are 3D poses that you can read out of these images. And if we cluster them, we'll discover that, okay, every time we see cups, these are the types of hand poses that are being used. And there can be more than one, but we'll find whatever the consensus poses are. We can do the same for any other object. Here are some hammer instances and the hand poses that were found. Okay, so now we have a visual prior. Imagine doing this for all sorts of objects in the video. And we build next a deep reinforcement learning network that is going to iterate between the agent seeing the RGB, the depth, the predicted affordance maps, like I was showing earlier. That's all on the left-hand side in green. And then receiving rewards as it does well at getting objects off the table. And that reward, the key for what I'm showing you now, is augmented by what's in that red box, this pose prior. Okay, so here's where the visual stuff comes in to influence the action, because we're going to say you get a reward for getting the object off the table, but you also get a reward if you are using a hand pose that is human-like. You also get a reward if you are grasping near or touching the visual hotspot affordance regions. Okay, so here's where that video informed prior, or VIP, comes in for our Dex VIP model. Okay, so you imagine training this then for the agent to get experience with new objects and zero in on the places that are going to be most effective to grasp them, even before it has its own physical experience. And what I'm playing you now are 6 different objects that this hand is encountering over time during training. And you'll see, initially bumbling, and then this RL agent is starting to pick up better postures that connect with the object and even grasp it in relatively human-like ways. Right? And what happens then is we can see how this people prior from video does accelerate learning and lead to better generalizing policies. This chart summarizes that because you have on the bottom axis the amount of training time and experience. On the vertical axis, you have the success rate. So a really good curve here would shoot up fast on the left-hand side of this plot. The curves I'm showing you, ours is in blue. The one just below it is an ablation where we took away the human hand pose prior. And then the yellow one is an existing state-of-the-art method that blends imitation with reinforcement learning, where the imitation tries to imitate the human postures given from a mocap VR hand pose over time for the very objects of interest. And then you have some simpler baselines below that do things like just try to touch the object. We reward you for that. That's green. Or try to touch the object near the center of mass of the object. That's in red. And what this shows is indeed you can learn faster from this video prior coming into play, and that the ultimate policies were more accurate, more successful, meaning we get the objects off the table more frequently. All right, so let me show you just a couple instances then for a couple objects. Here's back to the cup, and on the right-hand side, you see our model, and you can see a snapshot on the bottom of the human hand pose it's trying to mimic, or at least that it gets bonus reward for doing. And you can see that it was able to pick this up better than the baselines and to do it in a fairly human-like posture. Same thing for here for the hammer. Okay, so you can see the progress that we're making, bringing in that human experience to affect the agent action. Now, I've shown you so far how we can start to build up visual affordances, learning by watching people, how we could push that plus what we understand about human poses in video to accelerate and improve the dexterous robot grasping. And then the final piece, I want to move up a level in granularity from the fine-grained motor or motion control of the hand to more abstracted action space of agents that move around and try to solve what are called visual planning tasks. So they're going to be in household environments, and you want them to solve sequential tasks that typically involve interactions with multiple objects in sequence. And now the action space, rather than the dexterous hand, is going to be the ability to move in the space and pick up and put down objects. Okay, so in that context, we're interested in being able to, again, shortcut the agent learning and scale it up by observing how people do things. Let me show you this third example. I mentioned that these are going to be tasks that require sequences of steps and multiple interactions. So for example, asking an agent to be in a new unmapped space and figure out how to wash the dishes. Now, I think you can see, perhaps right away that the chance of, stumbling upon a good solution to something like this, say with reinforcement learning, is going to be low. It's going to be challenging. And that's because there's a number of preconditions that have to be met to achieve the goal state. And it involves multiple objects. For example, here, if I say wash the dishes, then we're going to need a combination of things to happen, that the agent's at the sink, that it's holding a sponge, that there's a dirty dish in the sink, that the faucet's on, that there's soap nearby, and so on. Okay, so these are, easy for us, but complex interactions to start to build up if you want, especially to scale up robot learning to have a task general kind of behavior. So here too, we wonder, can we discover these activity contexts, the things that would enable many actions or progress on different actions from video? Here's an egocentric video of a person doing kitchen actions. And yeah, so if we could look at how humans bring objects together, the premise is that this would give us an advantage for the types of configurations of objects, meaning objects that come together at the same time in use, that tend to lead to forward motion in a task. Like all these things that were happening here, like I just described about the dish and the dirty dish and the soap, etc. And very important to call out here is that we're going to address this in a task agnostic way. So we're not looking to imitate how a human washes dishes, although that's interesting. We're actually looking for something more general. We want to build up priors of how people tend to use objects together to do any task, such that when the robot has a new task for which there is no explicit human demonstration, we could nonetheless have preferences for the kind of things to attempt to build up the steps in that sequential task. Okay, so in short, we're not trying to imitate human behavior, we're trying to imitate human skills, and so that we'll bring those skills into solving new robot tasks. So let me say a little bit then how exactly we do it. We're going to, again, take in the wild video, like the ones I've been showing, and discover which objects together enable activities. Then we're going to leverage those, what we call activity contexts, for interaction policy learning. The key insight is that for a human, for an agent, there is going to be valuable interactions with some objects that only become valuable when other objects are nearby. So for example, if I'm holding a pan like this robot here, there's going to be a lot of doors, figuratively speaking, doors that get open if I bring it over to, say, the stove or maybe even the faucet, but less real activity enabled if I just bring a pan over and start interacting with a book or a bottle. So the idea then will be pick up these associations from video, from human action, and then ask the agent to intelligently move objects in the environments to places where compatible things are close before they attempt to perform an interaction. So we take egocentric video, we detect objects in the view of the person doing actions. We care only about those that are involved in interaction. So it's not about spatial proximity, it's about use, human use. And then we build up associations for any given object. So it's, in my previous example, the pan being highly compatible with the stove and sink from human action, but less so with something like a bottle or a book. And then we'll use these to prefer exploration steps in this interaction policy that will achieve as much of these high-powered compatible activity contexts as possible. Okay, so this is the approach from video to the interaction agent. And as you might know from the picture, we're going to be exploring this in the AI2 Thor environments, where we have agents that can both navigate and pick up and put down and use objects. So we build up those associations, as I mentioned, from the ego video. Things will come out to say, that knives with carrots were achieving certain interactions, that the sponge with the dirty pan, and so on. And this, what you're left with is a score for every pair of objects, saying how they can be brought together for an activity. And then we tackle it or we bring this into bear in a task agnostic way. So we have a family of visual semantic planning tasks in AI2 Thor that we want to address. Things like store something, heat something, clean something, throw something away. And we enter the environment not having watched people do each of these things, but instead having watched people do whatever their behavior was in the Epic Kitchens ego video. And now we'll augment the reward to say, not only do we reward the goal state of any of these tasks, but we also reward achieving these compatible activity contexts from human use. Okay, and when we do this, kind of like the plots I showed you before, but now, different setting, different baseline, we're seeing that we can accelerate the learning and have more successful policies. And that's compared to state-of-the-art exploration models, as well as the use of more co-occurrence-based scene priors. Okay, so I've shown you about some of our steps towards agent action being informed by human activity. The last slide I want to show you here is highlighting a new data set that we're part of together with 14 other institutions. This is called Ego4D, and this data set will further support the kind of work I'm talking about and hopefully much more. It's in the wild, egocentric wearable camera data from almost 1,000 different people around the world. And it's showing you these daily life activity glimpses, indoors, outdoors, a lot of complex hand-object interaction, even people and animal interaction, that this is a public data set to support research and the benchmarks that come with Ego4D that we've proposed, as well as things like I've just been showing. And I'll finally emphasize it's a multimodal data set. The video is the core, but there's also audio, there's 3D scans for portions of the data, IMU, stereo, and multi-camera capture. Oh yes, I said last slide, but I remembered that the chairs had asked for a little bit of dirty laundry. So here's the ones I'd highlight for challenges in the work I just described. Sim-to-real transfer, this is important and will require continued work, although there's a lot of encouraging results in the literature so far. In 3D object modeling in the presence of hand occlusions is non-trivial, and yet it's the kind of thing we want to build on for the models I just showed. And then you may have noticed that the absolute success rates for visual semantic planning is still low. There may be 20% kind of success rate for these sequential interaction heavy tasks. And so pushing on that remains very important. All right, I will stop here and we'd be glad to have any questions or comments.